We have come to the point of talking about rational functions. We've talked about rationals a little bit, but in this unit we get to take a little bit of a deeper dive. So as we introduce rationals, I'd like to start just by looking at and graphing what we would consider the base graph for rational functions. And then through this discussion, we'll be able to bring up the idea of domain again. And hand in hand with domain, we'll go something called the vertical asymptote. So let's dive in. Let's consider the function f of x equals 1 over x, because rationals are basically fancy fractions. So when I hear the word rationals, you can think of them as, like I said, fancy fractions. So we've got basically a variable involved in the denominator of the fraction. If it's a variable in the numerator and a number only in the denominator, then technically it's not going to be rational. It could simplify to linear or quadratic or something like that. But let's take this example of f of x equals 1 over x. And I want to look at its graph just to start getting familiar with a very important characteristic. So one technique we know to create a graph from scratch with a new type of function is just a good old XY table. If you're unfamiliar with a base graph of a function, just choose a variety of inputs and a variety of outputs will then result. So let's just try, I'm going to make room for 7 different values. So -3, -2, -1, 0, 1, 2, and 3. And to find the outputs, we just need to use the rule of the function here, which says take whatever you input and make that the denominator of a fraction, so 1 over the input. So if I input -3, I get 1 over -3. And for the folks who like decimals, that's about -0.33. Input -2 and I get 1 over -2, which is -0.5. Input -1 and we get 1 divided by -1, which is -1. Input 0 and we get 1 over 0, and oops, that's a problem, right? Division by 0 is undefined. So we're running into the problem that can happen with rationals. Input 1, 1 over 1 is 1. Input 2, 1 over 2 is 0.5. Input 3, 1 over 3, again, we could think of that as roughly 0.33. So I'm just going to plot those 7 different values, or at least try to, and then we'll notice something about the graph. So as I make space, I need all the way to -3 and +3 on my x-axis based on the inputs I chose. And for the y values, those ones are a little smaller, right? So I'll just try to scale this a little bit in the y direction. So I'll let this be 1 and this be -1, because I can tell I'm going to have to plot some values in between. So to plot these points, let's start with when x is -3, the y value is a -1/3. So I'm going to say a -1/3 is roughly in here. So that would be my first point I'll plot, -3, comma, -1/3. Then when x is -2, we're going to drop halfway down towards -1. So this is -2, comma, -1/2. And then when x is -1, y is -1 as well. So far I've got these 3 points, and I kind of feel like they're creating a little shape down in that third quadrant. Now, when x is equal to 0, the function is undefined, and so this actually tells us that we need to avoid ever touching when x is equal to 0. So I'm going to go ahead and note x equals 0 as a vertical dashed line that we'll never actually touch. We'll talk a little bit more about this, so hang tight with that one. And then my next 3 points say when x is 1, y is 1. When x is 2, y is a half. And then when x is 3, the y value is 1/3. So just for a little bit of indication of my tick marks, there that is. Okay, so I hope it seems somewhat intuitive that this graph is actually pieces. So if I do a rough sketch of connecting the points on each side of that dashed line, you'll see I get pieces kind of like this. So that would be a rough sketch of our function. So this is the graph of f of x equals 1 over x. And probably the most striking characteristic of this graph is the fact that it is not continuous like the polynomial functions we saw in the last unit. Polynomial functions we could draw, smoothly, never lifting our pencil, but here we end up with two pieces and then that vertical line. So let's talk a little bit about domain. Domain is something we've discussed. We've even discussed it in light of rationals, knowing that we don't want to divide by 0. So notice that the value of x that caused us to divide by 0 in this particular function was when x is 0. So that means the domain has to be everything but 0, right? So everything but 0 is acceptable inputs. So I can write this in two ways. One way would be to say all x are good such that x does not equal to 0. That would be your good old set builder notation. And then another way to express that domain using interval notation would be to say from negative infinity to 0, jumping over 0, picking back up from 0 to infinity. So either one of these notations is absolutely great. As you all know, you can take your pick. The first, again, being the set builder notation, and the second being the interval notation. So now that we have domain on the board here, I'd like to talk about the vertical asymptote. So I'm going to write out the vertical asymptote. And an easy way to think about the vertical asymptote is whatever the domain cannot include, that value is the vertical asymptote. So as we saw from the domain, we cannot use x equals 0. Therefore, the vertical asymptote is x equals 0. Basically, the domain plus the vertical asymptote will cover all real numbers as inputs. So if I look back on my graph, that red dashed line is now what we'll call the vertical asymptote, which I can abbreviate here as VA. So the vertical asymptote is the line that the graph will never touch. You can have more than one vertical asymptote, as you guys are probably aware, depending upon how complex the denominator is. So we'll use this as our introduction, and then in the next video, let's look at some more complicated cases of the domain and the vertical asymptote. So even if we don't continue building the graphs, we can still analyze the functions in terms of the domain and the vertical asymptote. So we'll do that in the next video.